All right, guys, good morning. Today we're going to do chi-square goodness of fit test. All right, so this is going to be a little bit of a math lesson. And so today we're going to find out what is the purpose of the chi-square test and how do we actually perform a chi-square test. Chi-square testing is used in hypothesis testing. This is used by scientists to reject or fail to reject statistical hypotheses. It also helps determine if the differences in numerical data are to the independent variable or simply just due to chance. There are going to be two types of hypotheses we're going to be talking about. We're really going to be focusing on the null hypothesis today. And this states that there is no relationship or no difference between two groups of data in an investigation. Another type of hypothesis is called alternative hypothesis, and this is one of many possible hypotheses that states observed results are due to non-random causes. When do we use the chi-square goodness of fit test? It is used to determine if there is a significant relationship between two groups of data. The two groups of data that we're going to be talking about or using, it's going to be observed outcomes versus expected outcomes. Observed outcomes are compared to expected outcomes to see if variations could be due to chance. We're often going to use the chi-square goodness of fit test in genetic crosses, but it can be used for other analysis as well. So here's the formula, and this formula is going to be given to you in your AP biology formula sheet. So if you have your laminated sheet next to you, go ahead and get that out. Have it handy because we will be using it today. Don't get overwhelmed by looking at the formula, all right? I know it looks complicated, but it's actually a lot easier than what it looks like. And so let's figure out how we're going to use this formula to see statistical analysis in genetic crosses. So here is my question. Do seed color and seed shape assort independently? Well, I'm going to be looking at two phenotypes here. I'm going to be looking at seed color. There are two types of seed color on my corn. I'm going to use the allele R to represent seed color. So capital R is purple. That means purple is the dominant trait because I'm using a capital letter. And lowercase r is yellow. That means yellow is going to be the recessive trait. The other trait that I'm going to be looking at is going to be seed shape. All right, this is the other phenotype I'm going to be looking at. And I'm going to be using the allele S, all right, to show this. A capital S is for smooth seeds, all right? That means smooth is dominant because I'm using the capital letter, and lowercase s are for wrinkled seeds, and I'm going to be using the lowercase s, which means that it is a recessive trait, all right? Off to the side, you're going to see different types, yellow and smooth versus purple and wrinkled versus purple and smooth and yellow and wrinkled. That way that you know what I'm talking about in just a second. So the very first thing that we're going to do is we're going to count the observed values, all right? Literally, guys, pretend you have this piece of corn in front of you. I know I did, all right? And I went through and I counted every type of phenotype combination that exists on my corn, all right? That means I counted every single seed, right? In total, I counted 118 purple and smooth seeds. I counted 29 purple and wrinkled seeds. I counted 33 yellow and smooth seeds, and I counted 6 yellow and wrinkled seeds. All right. And so the way that I got these observed values is by literally grabbing this corn and counting each of those seed types. All right. The next part is to determine the expected values. And so this is where we're going to use our dihybrid cross knowledge and put it into action, all right? So the corn I used to count the observed values, came from a cross that was of completely heterozygous plants. Remember, hetero means different. And so both of my corn plants, right, that made that corn, okay, had two different size letters. So big R, big S, little s, all right? In order to find the expected values, I need to do my dihybrid cross. Remember, my first step before setting up my Punnett square is to do the rainbow method, or to FOIL, or to distribute, whatever you want to talk about, and you need to find all the possible allele combinations. Because the parents' genotypes look exactly the same, their allele combinations are exactly the same. And so we'll see that big R goes to big S, big R goes to little r goes to big S, little r goes to little s. I set up each parent, one on top and one on the bottom. Remember, there are two rules when filling in my dihybrid cross. Same letter stays together, capital always in front, all right? Because I started with the R's first, okay, I'm gonna just keep that going in order to have a specific format. I went in and I filled it all out. What I ended up doing is I colored in the boxes that had the same phenotype. So big R, big S has the same phenotype as big R, big S, little s, or big R, big S, or big R, big S, little s, right? That is always showing that dominant trait of purple and smooth. After that, I went to color in green my purple and wrinkled. Then I colored in my yellow and smooth. And finally, I have one yellow and wrinkled, which is the purple box off to the corner. I wrote down this information onto the next slide. So you're going to see that I had 9 purple and smooth, 3 purple and wrinkled, 3 yellow and smooth, and 1 yellow and wrinkled, just like I had mentioned before. And so how do I put this into an expected value? Well, guys, let's look at the purple and smooth first. I had 9 out of 16 squares show the phenotype purple and smooth. And so what I'm going to do is I'm going to multiply that by the total of seeds observed, which was 186. So 186 times 9/16 equals 104.6. I did that with this with each of my seed types, okay? So 186 times 3/16 for my purple wrinkled, 186 times 3/16 for my yellow smooth, and then 186 times 1/16 for my yellow wrinkled. And the numbers underlined in green were the values that I got when I plugged those numbers into the calculator. One thing that I like to do is I made sure that my expected values have the same total as my observed. So you're gonna notice that my totals match, right? 186. And so that's a quick check that you should do at the end of your math when you're getting those expected values. Something that's really cool, most of the time, they're gonna give you the expected values, and so you won't even have to go through all of this, but hey, maybe you will. We don't know, right? And so that's why I'm showing you how to find these right now. Once we find those expected values, all we have to do, y'all, is plug in the numbers, okay? And so the chi-square formula is the sum of observed minus expected squared over expected. And I'm going to do that for every phenotype. So I'm going to start off with my purple and smooth. 118 minus 104.6 squared over 104.6 gives me 1.717. Literally plug that into your calculator. That's what you're going to get. And you can do this to check, right? Make sure that you know how to use the calculator. This is a great time to pause and see, hey, can I actually square on my calculator? Am I doing this correctly? All right, check your math with my math. Then I'm going to do purple and wrinkled. 29 minus 34.9 squared over 34.9 gives me 0.997. Going on to my yellow and smooth, I have 33 minus 34.9 squared divided by 34.9. So that's going to give me 0.103. And then finally, my yellow and wrinkled, I have 6 minus 11.6 squared divided by 11.6, which gives me 2.703. When I add all those values up together, I get 5.52, right? That is my chi-square, okay? 5.52. And so what we're going to do is we need to use that number and see what it is in my chi-square table, all right? But before I do that, I need to figure out my degrees of freedom. And so what are degrees of freedom? Degrees of freedom are the estimate of the number of independent categories in an experiment, where the degrees of freedom equals n minus 1. And remember, n is just your sample size. And so looking at my phenotype, what was my sample size? Well, 4, because I had 4 possibilities of phenotype. My first one, purple and smooth. Second, purple and wrinkled. Third, yellow and smooth. Fourth, yellow and wrinkled. Therefore, 4 minus 1 equals 3, and my degrees of freedom are 3. Well, where am I going to use this? You're going to use this when looking at your chi-square table, okay? Now, you're going to notice that there's 2 p-values, and the p-value is usually going to be given in your practice problem. In this example, we're going to be using a p-value of 0.5. And so what this does is I go to the p-value, 0.05, right, which is my first row, and then I go to the column 3 because I have 3 degrees of freedom, and you're going to notice that my critical value is 7.81, all right? And so what am I going to do with this number? Well, I'm going to compare it to the number that I got in my chi-square formula. If the chi-square value is less than the critical value, you're going to say that you fail to reject the null hypothesis. Now that sounds weird, fail to reject, right? All that means, y'all, is I'm going to accept the null hypothesis, okay? And so if they use the word accept null hypothesis or fail to reject the null hypothesis, it means the same thing. Up next, if the chi-square value is greater than the critical value, then you're going to reject that null hypothesis, okay? And so because my chi-square value was 5.52, it was actually less than the critical value of 7.81. And remember, that critical value came from the table on the previous slide, all right? Therefore, we fail to reject the null hypothesis or accept the null hypothesis. So what does this tell me? It tells me that there's no relationship between seed shape and seed color. Therefore, the 2 traits are assorted independently of each other. All right. All that's left to do is practice. So go ahead, use this video as well as the slides that I posted on your teams to help you. You have 1 practice problem, and it's your turn. Go ahead and practice doing chi-square analysis. Have a great day.